One of the equations that is used in statistics, and we will be using quite a bit when it comes to talking about testing hypotheses, is Bayes' theorem. While it looks like there's a lot of terms and it looks complicated, it actually only consists of a few different numbers. And not all those numbers are even independent of each other, that if you know one, you will know the other instantly. In fact, if you work it out, you'll find there are only 3 numbers you really have to input. So let's take a look at what all these terms are. Ultimately, we have this big, looks like complicated thing to have it equal this. This is the probability of A given B. That's what this notation means from probability theory. So, probability of A given B. This what we call basically, in the end, our final or posterior probability. The reason we give it this name is that it's saying, okay, I have some hypothesis A. Whether it's you have a certain disease, or whether a certain theory in physics is true, etc. Whatever that hypothesis is you're testing, you're saying, what's the probability of that being true, given that you have some information, some experiment, some evidence B. It's ultimately designed to say, all right, I have some belief. I've gone out, I've gathered this information. How does it affect how likely my belief is now? And so the reason it's called the posterior or final probability is that's the number you pop out with after you have considered evidence B. So before you go and consider the evidence, you have to say, all right, well, how probable was my hypothesis in the first place? That is what we call probability A here, the prior probability. So this is how likely you think your hypothesis is true before you gather any more data, before you find any more evidence for or potentially against it. So that number is, because it's a probability, it has a value anywhere between 0 and 1, or if you prefer, 0% and 100%. If the probability is 0%, that basically means it's logically impossible. And if you plugged in a prior probability of 0 here into this equation, well, no matter what evidence you find, no matter what else these other terms are, the final posterior probability has to be 0. Becomes kind of boring then. Conversely, and we'll see when we play with this a bit, if your prior probability is 100%, that it is logically impossible for it to be false. Say 2 plus 2 equals 4. Well, that's going to be the case. Then you actually find that posterior probability will also be 100%, but we'll see that with some numbers later. But for any sort of probability about things in the real world where we don't have logical certainty, that probability is somewhere between 0 and 100%, never actually 0 and 100%. Now, we also have this term that we have P with a minus sign in front of the A. P not A is what we call that. And this is basically the probability then that your hypothesis is false. Well, in this case then, from basic logic, that there's either something is itself or not itself, true or false, the probabilities have to add together to 100%. So if there's a 50% chance you're right, there's a 50% chance you're wrong. If there's a 90% chance you're right, there's a 10% chance that you're wrong. So basically, if we know what the prior probability of the hypothesis being true, then we know that the other probability, the probability of being false, is just 1 minus that probability, or 100% minus that probability if you want to do everything in terms of percentages. So this is just about, all right, how initially likely is it that you're going to be right before you even do any testing? So how about the other terms in this complicated looking equation? So in the same way where the posterior probability of A given B, that sort of terminology, we also have in this setup P B given A. What that means is, what is the probability of seeing evidence B given hypothesis A? In other words, if you see some bit of evidence B, how likely are you to expect that if your hypothesis is true? So, for example, if you are testing to see if there's a disease someone has, and you do a test, and it comes back positive. Well, if you actually have the disease, how likely is it that you would get a positive result? It may not necessarily be 100% because tests aren't necessarily perfect, but you would say, okay, that's at least definitely consistent with what I would expect. That also, of course, means there's this other probability we see here, B given not A. So what this really means is, okay, we need to consider what's the probability of seeing evidence B if A is true? What's the probability of B given that A is not true? So to use an example, let's say it's early in the morning and you find that the ground is wet. There's two different hypotheses you could think of. One might be, oh, it rained last night. Okay. If it rained last night, you would definitely expect the ground to be wet. So let's say then that A is it rained. And evidence B is ground is wet. Okay, so in that case, you would expect that sort of evidence B, given that it rained last night, so you would think this probability would be rather high, maybe even close to 100%. On the other hand, though, given the same evidence, is it possible that the ground could be wet even if it didn't rain? Absolutely. Maybe your neighbor's sprinklers went off in the morning, and that's why the ground is wet around you. So that's why we have to consider both probabilities of the evidence seen on either hypothesis, because we could explain the same evidence B with both our hypothesis and a competing hypothesis. Now, there might be evidence that doesn't fit one hypothesis more than the other, or it could be the case that we have some piece of evidence that only fits one hypothesis and is absurdly unlikely on the other. Either way, that's the sort of numbers we would be plugging into here. I should note, though, that there is nothing that says that these two probabilities have to add up to 100%. In fact, you could have it so the evidence is completely consistent 100% on either hypothesis. So, for example, your hypothesis is it rained last night. Suppose your evidence, let's call it B prime, is that the world exists. Well, that's pretty much expected whether it rained last night or not. So if you were to plug this in, well, you would expect basically, okay, seeing that the world exists if it rained last night, that's 100%. The world existing even though it didn't rain last night, that should also be pretty much 100%. It's not really evidence of either hypothesis. And that's the important thing of why you need to consider both of them in this equation. And it's the case then, oh, if this is 100%, this is 100%. If you were to add them together, you'd get more than one. You'd get more than 100%. So there is definitely no thing that requires these two to be added together to give 100, like we did with the prior probability and its probability of being false initially. What this means then is that there are just 3 different numbers in this entire equation that you need to have. You need to know what is your prior probability, the probability of seeing the evidence given your hypothesis, and the probability of seeing the evidence that given your hypothesis is actually not true. So there's only actually 3 numbers. P not A, the probability of the hypothesis being false, is automatically calculated. And for example, we see this complicated equation here, but this term right here and this term right here are exactly the same. So let's try this with an example. Suppose you have a random person and you want to consider how likely is it that they have the common cold. How probable is it that a random person has the cold, and you want to look at their symptoms and then figure out, oh, do they actually have the cold or is it something else? So for example, let's just say a random person you see has a 1 in 20 chance of having the cold. So that would suggest that if you go out, 1 in 20 of the people you see right now have the common cold right now. That's probably a bit high, but we're using this for illustrative purposes. You definitely know it's not 1 in 2, but you also know it's not exceedingly rare either. There's seasonal fluctuation, so let's just say this is a reasonable average, that 1 in 20 people are going to have the cold at some given time. Now, of course, that also means it's rather probable that they don't have the cold. So we say not cold, or opposite of having the cold. Well, that should then be 19 out of 20 people you see will, well, not have that particular sickness. Okay, so that's just priors, though, but you do want to consider the evidence, because if you don't, well, then you're going to, any person you run into, you're going to say, well, they're probably not sick, and if you don't consider the evidence, then there's going to be a lot of sick people that you're just ignoring. So we need to consider, all right, what should we look for as evidence? We know that if you have the cold, there should be certain symptoms. So let's consider the symptom that you are sneezing. So the probability of a sneeze. And we have to consider what's the probability that you're going to have a sneeze if you do have a cold, and the probability that you are sneezing if you don't have a cold. Well, we know that basically if you have a cold that there's probably an increased chance that you're going to be sneezing. It's probably better than 50%. Let's say a significant fraction of people with colds are sneezing. Let's say 80%, or that is would be, let's say, 8 out of 10, 80%, whichever fraction you find to be the most useful. Now, we also know that people will sneeze even if they don't have the cold. How often does that happen, that people have the cold, are sneezing and they don't have the cold? Maybe they're sneezing because they have some other disease, whether it's rarer than the cold or not. Or it's just hay fever season for them, something like that. So let's just be somewhat inventive and say 1 in 10 people who are sneezing do not actually have the cold. So that way, if somebody is sneezing, then it's, not too crazy to think that they don't have the cold, but it's maybe a bit rarer. That's 10% here. So if we try plugging this into Bayes' theorem, then we could say, all right, well, what is then the probability that you have a cold, given that we got a sneezer here? All right, so we just have to plug in the various numbers from Bayes' theorem. So we can plug in, for example, our value of 8/10 as the probability of seeing sneezes given colds, probability of there being a cold, 1 in 20. That's our numerator already, so then in the denominator, repeating of probability of seeing the evidence given, having a cold, probability of having a cold, and then adding the part of probability of seeing sneezes when there's not a cold, times the probability of not a cold. Plug in all of that, do the arithmetic, and what you find is that the probability this person actually has a cold if they're sneezing, given our information above, is, doing the fractions, we get 8/27, or if you prefer as a probability, and I think that would be easier to see, as 29.6%. So better than a 1 in 4 chance, and that is definitely higher than our prior probability up here of 1 in 20, or 5%. But of course, in that case, if we look at this probability, we'd see, oh, about 30-ish%, that's less than 50, so actually, if anything, this person probably doesn't have a cold, if we're just using this evidence. So that one symptom alone of just sneezing, given these numbers and believing all the numbers we plug in, would still say the person probably doesn't have a cold. Now, we could go through the exact same operation and use different evidence. So maybe the person not only is sneezing, maybe they also have a runny nose, they have a fever, etc., things like that. You can throw in all of those probabilities and do the same operation over and over again. you could use this as your prior probability, and then every time you can plug in for new evidence, saying, well, how often does somebody have a runny nose if they're sneezing and they have a cold, etc. You can rinse and repeat and then make it very probable that somebody has a cold and then treat them. Or, of course, conversely, you could say, well, these symptoms are missing, and so they probably don't have a cold. But no matter what, you'd be plugging in the numbers in the same sort of process. Now, let's take a look at a couple of interesting scenarios. One thing I mentioned were results if, for example, PA equaled 0, if there was no possible chance of the hypothesis being true. Well, we see if that's the case, that we're basically plugging in 0 here, and you'll have then 0 in the numerator, and the denominator here will not be 0. This will be 100%. This will probably be something, well, it has to be something other than 0. So you'd have 0 divided by something not 0. The posterior probability has to be 0 as well, which basically means if something is impossible, there is no way that evidence of any type, evidence B, could prove otherwise to you. But like I say, you have to have absolute certainty that something is impossible. Now, we do have things like that. For example, there's no such thing as a round square. That's a straight-up contradiction. You couldn't have that. And in that case, there's no way you could possibly find evidence for such a hypothesis. It's impossible. Now, also consider then the case that probability A is 100% or equals 1. In that case, then, that also means the probability of not A is 0. Again, just because of our definitions of how these things work. So, in that case, if PA is 1, P minus A is 0, this entire term is just canceled out, and the numerator and the denominator are exactly the same. So, something divided by itself is just 1. So that would imply then that our posterior probability is equal to 1, or 100%. Again, what that would mean then is if you have 100% certainty in the truth of your claim, no evidence is going to change that. It's always going to be 100%. But again, this of course assumes you have 100% certainty, and that requires logical certainty, such as 2 plus 2 equals 4, or all bachelors are unmarried. Very, very rare you're going to have that, and in the real world, you definitely won't. Now, one other thing that would be a bit interesting, and it comes to looking at the evidence. So specifically, when you look at evidence B, you have to compare how well it fits hypothesis A versus hypothesis not A. And here's why. Let's suppose that actually the two are the same. So suppose that the probability of seeing evidence B on A is the same as the probability of seeing the same evidence B on its opposite, not A. Then in that case, we would basically see some things canceling out. After all, then, if these two terms are the same, and these terms right here, of course, are obviously the same, I could divide out the numerator and denominator by both of those, and so I would end up getting something looking like this. I would have PA divided by PA plus P not A. And of course, from our definition that PA plus P not A is supposed to equal 1. That's all the possibilities. Something being true and it being not true. So this has to add up to 1, so we're just dividing by 1. Pretty boring. So in that case, the posterior probability is just equal to the prior probability. In other words, if the evidence fits both your hypothesis and some other hypothesis equally well, then it doesn't change your probability at all, which makes sense. If your evidence doesn't actually support your position over any other one, you have no more reason to believe it's more true than false than when you started. So, to highlight and review, there are three facts basically you need to consider when using Bayes' theorem. Your prior probability, the evidence expected on your theory, and the evidence as expected on an opposing theory or against your theory. And you have to always consider these three things if you want to say how true or how plausible your belief is. You have to consider, first off, well, how well does it actually fit what you know already before doing any testing? How plausible is it? What background reasons do you have to believe it's true or false? And that'll have a value anywhere between 0 and 1, and unless it's something you can logically prove or disprove, it's going to be somewhere between 0 and 100%, not actually 0 or 100%. Then you'd want to see, okay, I do some sort of test, I gather some evidence, and I see how well do I expect to see that evidence if my theory is true. And I also have to check and make sure, okay, does that same evidence fit any other theory just as well? Even if it doesn't fit another theory perfectly, how well does it fit? How expected could I see this evidence if my hypothesis is actually false? If I think of these three conditions and I diligently find what the values are or what they might be around, I can then stick that in and find what is the posterior probability, which is basically how likely is it to be true that such and such a statement or such and such a theory is true.